So thinking about something that's a little bit more complicated, like at least one, that's a term that gets thrown around. The probability of getting at least one, and let's stick with our queens example, getting at least one queen, plus what would the complements of at least one be in order to add up to 100%? And so let's think about it in a scenario where we have 3 draws. So we have a deck of cards. We're going to pull out, so we have 3 draws. We've got this deck of 52 cards. And I'm going to pull out a card. Is it a queen? All right, we're going to throw it back in. Pull out another card. Is it a queen? Throw it out. Put it right back in. We're always keeping that deck the same. We just keep replacing that card again and again. So if I do that 3 times, what's the probability that I get at least one of those 3 cards as a queen? Yeah, what do you think?
I think the probability might be like the chance of just getting one queen. So wouldn't it be just 48 out of 52 plus 48 out of 52 plus 3 times 48 out of 52?
Well, let's think about that. At least one queen. So that means on 3 draws, you're right that it could be getting one queen. But there's multiple ways of getting one queen, right?
Yeah.
You could get a queen on the first one and a not queen on the second and third. That's getting one queen. You could miss on the first and get your queen on the second and miss on the third. You could miss the first 2 times and then finally get a queen. So you see how these 3 options are all displaying how to get one queen. But we're concerned with at least one queen. So this is just the beginning. So you could either get one queen, or you could get 2 queens, or you could get all 3 queens. Which means now we need to think about getting 2 queens, right? So if we were going to get 2 queens, you could get a queen, and a not queen, a queen, a not queen, and a queen, or a not queen and a queen and a queen. There's going to be a lot of possibilities here, and this is going to demonstrate, I think, do I have all the options there? Mm-hmm. That this demonstrates getting 2 queens. So now we've covered 1 queen and 2 queens, and then we would have to go in and do getting 3 queens. Queen, 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 straight away. So there's these, you can see the spread is starting to grow. Finding at least 1 queen would be figuring out the probability of this, which is getting a queen. We said that this was 4 out of 52. And then getting not a queen is 48 out of 52. And not a queen is 48 out of 52. So that we're going to have to, multiply those probabilities. And then do that again here, and do it again here, and again here, here, and here. So we can see at least 1 is not as simple as something occurring and not occurring. So you're right, we could do it this long way, give ourselves a headache, and eventually get that right answer. But let's remember this rule of complements, that 2 things must complement each other to cover the whole spread. What could possibly complement at least 1? Let's think about this graphically. Let's try and draw an image. If we did 3 draws, what are the options? I could either get no queens, I could totally, have no luck and get 0 queens, or I could get lucky once and get 1 queen, I could get 2 queens, or I could get 3 queens, right? That covers the whole spread. So at least 1 queen. Which options on my graph does that cover? Getting at least 1 queen, well, that's going to be getting 1 queen, but getting 2 queens also counts as at least 1, and getting 3 queens counts as at least 1. So at least 1 covers the spread between 1 and all queens, right? Because over here, in 3, that's getting all queens. That's lucking out all 3 times. So if we want to cover this entire spread, to cover all of our options, what would complement at least 1 in order to add up, when added together, equal 100% of our options?
No queens. Then that's the only other thing.
The only other thing that's blank here is this slot, no queens. So no queens plus at least 1 queen covers the whole spread of all your options you could get. 0 queens, 1 queen, 2 queens, 3 queens. We've covered all the possibilities. So those two together, added up, equals 100%. So how can we, let's fill in the blank on this rule then. The probability of getting at least 1 plus what equals 100? Equals 1.
None.
1 plus none. The probability of getting none. Not getting a single 1. So this is a golden rule that we're going to carry with us now. The probability of getting at least 1 plus the probability of getting none equals 1. So let's think about this with our example. For the probability of getting at least 1 queen on 3 draws. Let's go back to this example where you did 3 draws. We could do it the long way like you said, or we could kind of backtrack. So what's the probability of getting no queens? That seems easier to find, right? So the probability of getting no queens, how would we do that? So to get no queens, that would mean we would have to not get a queen on the first, not get a queen on the second, and not get a queen on the third. So what's the probability of those 3 events happening? Well, not getting a queen on the first is going to be 48 non-queens out of 52, right?
Mm-hmm.
And on the second draw, it's still 48 non-queens in our deck out of 52 cards. And on our third draw, it would still be 48 non-queens out of 52. So here, what I just solved in green is the probability of not getting a single queen. Getting unlucky all 3 times. And we're going to multiply those probabilities, right? Because we want these events to be seen all together. Boom, boom, boom. We want this and this and this. Not a queen, not a queen, not a queen all together. So here's the probability of not a queen. And if we know that this together with this equals 1, that's the best way to figure out at least 1, right? We can just kind of subtract this from our equation to solve at least 1. Do you see how that works? So the probability of getting at least 1 queen would be 1 minus no queens. So let's think about another, does that make sense? Any questions on this?
No.
Let's think about another tricky option that might not be apparent at first. Let's think about, and this is one that is not as commonly thrown around as at least 1. Let's think about getting not all. Well, let's first, if this one is tricky though. You know, it might not be coming home yet, right? Let's think about something we care about. We care about our grades, right? So just to get the concept home, that at least 1 and none equal 100%. So imagine that you're taking 5 classes and you want to be a straight A student, right? Everybody wants to be a straight A student. So if you're taking 5 classes and you're concerned with how many A's you can get, well, what are our options in 5 classes? You can either get straight A's, right? That's what everybody wants, to get all A's if you're taking 5 classes. If you have 5 A's, you have all A's. Or you could just miss out by 1 and get 4 A's. You get 3 A's, you could get 2 A's, you could get 1 A, or you could get 0, which is no A's, right? So here's the spread. So if we wanted to think about at least 1 A, at least 1 A runs from getting an A in one class, an A all the way to getting all A's, right? You could get 1 A, you could get 2 A's, you could get 3 A's, 4 A's, 5 A's, in any combination of your classes. You know, this 1 A, this 1 A could be, you know, an A in science, or it could be an A in history, or it can be an A in English. I mean, there's a lot of combinations, right? Just like I was showing before with that spread. With 5 classes, that spread would really start to grow on us. So this is very challenging to figure out. But what would the complement of getting what would the complement of getting at least 1 A be?
No A's.
No A's. You either get at least 1 A, or you get no A's. At least 1 A runs from 1 until 5. At least 1 A. And together, those would cover the spread of getting 100% of your options for A's on your report card. Does that make a little bit more sense? Yeah.
So would you say that in general, when you're trying to figure out the probability of at least 1 of anything, it would be easier to figure out the probability of none first and then just subtract it from 1?
Yes, that is definitely the way to think about it. That this is more complicated to find, right? This is a whole big mess. This is harder to find. It's not impossible, but it would just take a long time. You probably need a few pieces of scratch paper. Well, finding finding the option of none is easier to find, right? None, it will be, kind of one fast equation rather than a bunch of these, piling on one option as opposed to all these options that start to snowball on us. So the moral of the story is it's easier to find the simple option first, and then use that to find the complement of it, knowing that those two have to equal 100% of our options.
So complement's not the same thing as opposite, right?
Complements are not the same thing as opposites. What would be the opposite of getting all A's? Opposite now. Like in upside down world.
Nice.
The opposite of getting all A's is no A's. But as you can see, like in yellow, getting no A's and all A's really only covers two of our scenarios, right?
Yeah, it's the extremes.
Those are the extremes. So opposites are not complements. Opposites do not cover the whole spread. Complements complement each other so that you have covered all of your bases. Every possible scenario is covered by complements. Opposites are just extremes. So that's why those two don't match up in an equation. It's these two that match up, covering the whole range of possibilities. Does that make sense?
Mm-hmm.
So let's think about another tricky option. Back to our queen, pulling out queens in a deck of cards. Let's think about getting not all queens. So if we draw from a deck of cards 3 times, we draw 3 times, 3 draws, and we want to know the probability of getting not all queens. Well, let's think about it again, just like our chart. We could either get 0 queens, 1 queen, 2 queens, or we could get 3 queens. So 3 queens is all queens, right? That's getting 3 straight queens. All queens. And what if we were concerned with getting not all queens? Well, if you get not all queens, that means you could get, 2 queens and 1 non-queen. You could get 1 queen and 2 non-queens. Or you could get no queens at all 3 non-queens. So you can see that now in purple, this is not all queens. And that seems to be more complicated than just finding all queens, right? But together, all queens and not all queens cover the spread so that when added together, they equal 100% of our possibilities. Do you see how that works? So if we wanted to find on 3 draws the probability of getting not all queens, we could go through each long painstaking example, each way to get not all queens, or we could solve this easier one. What's the probability of getting all queens? Well, first we need to think about the first draw. What's the probability of getting a queen on the first draw?
4 out of 52.
That's right, there are 4 queens out of 52 cards. Now I put my card back and I'm drawing again. What's the probability of getting a queen on the second draw?
4 out of 52.
Exactly, the same thing, because the deck is the exact same. And now finally, what's the probability of also, ding ding ding, lucky winner, getting that third card as a queen?
4 out of 52.
4 out of 52. So I need to multiply these probabilities together, and this would get me the probability of getting all queens. 4 out of 52 cubed. So that's easy, right? We just solved for that. So we can use that and use the knowledge that there is a complement in order to find this tricky not all queens, right? So the probability of getting all queens, we said all queens is going to be 4 out of 52 cubed, right?
That's all queens,
That's all queens. And if we wanted to find the probability of getting not all queens, we could use this image to tell that, well, we know that together they add up to 1. So if we just subtract this little piece from the whole image, that's how we get not all queens. So the probability of getting not all queens is just 1 minus the probability of all queens.
This might sound like a dumb question, but you put the 100% there and the 1 there. if you did the 100%, that you have to use the 1 in that. When do you use the 100%? When do you
Oh
use the
yeah,
1?
so 100%. So this is thinking about these in terms of, we use the 1 when we're thinking about these as fractions, right?
Okay.
We said that we could use for chance that probability adds up to either 1 when we're considering things like decimals and fractions, or if you want to think about it in percentages, 100%. So it's easiest when you're figuring out these probabilities. The best way to do it is just think about them straightforward, just like we did in terms of your fraction.
Okay, because that's a fraction there, so you'd use the fraction there. I get it.
Exactly, yes. So this 100% is really just to kind of
It's
show
the
that's 100% of our options, or 1 if we're talking about these fractions the way that we are. Because, in order, 100% is the same thing as 1 for fractions. Does that make sense?
Yeah.
Good question.
Yeah, if we would use the 100%, if all those 4 out of 52s were changed to percents by multiplying by 100 or something.
Right, exactly,
Yeah, okay.
right.
And we're not doing that, because that's just,
That's going to be another mess. Good question, though. So, now if we wanted to think about this, so that's how we do it. There's the answer to our problem. And to relate it to something that we care about, let's go back to our example of grades. If I were thinking about taking my 5 classes, if I were taking 5 classes, we said that my options, I could either get 0 A's, 1 A, 2 A's, 3 A's, 4 A's, or 5 A's, right? And the complement, so not all A's, if I come home at Christmas break and I tell my parents, well, I got not all A's, that in their minds could be anything, right? Well, not anything, but it could be, oh no, she got 0 A's. Or it could be, oh, well, maybe she got 1 A, or 2 A's, or 3 A's, or 4 A's. The only thing that they know for sure is that I didn't get all A's, right?
oh yeah.
All A's. That's a roundabout way of telling my parents, I did not get this, I could have had any of these. Not all A's. And hopefully they'll assume, the better options. But, so not all A's complements all A's to cover 100% of the bases when added together. Does that make sense? That we
Yeah,
can see
it's
that
not
those are complements?
sometimes you think it's either all or none,
Right. When that's not really the case.
Yeah.
All or none are opposites on my scale, right? Those are the two extremes. But they don't cover the whole spread of all of my options.
Yeah.
The two complements here are not all A's, ranging from 0 to 4, and then all A's, that one option of getting straight A's, adding up to 100% of the options. So then let's add just one more formula up here as well that we're going to use. So the probability of not all A's, which is kind of tricky to find, plus the probability of what equals 100% of the options. What's the complement that we decided?
All.
All. Not all and all complement each other to add up to 100, to 1, to cover 100% of the bases. All and not all add up to 1. Does that make sense? So these are really going to be some key formulas that, using this knowledge and thinking about it in terms of covering our whole spread, we could find what is tricky by first finding the easy part and working backwards, rather than using 4 notebooks this semester, coming up with the probability of each individual scenario, right? Because getting, 3 A's, that could be an A in science, chemistry, and math, or that could be English, history, and science, or that could be, any combination, right? We would have to go through each and every scenario. Very tricky, very tricky. Not impossible, but very tricky. So why not use the simpler method of find the simple way and then work backwards to the complicated part? Yes?
So in general, if you start trying to figure something out directly and it seems like, oh, there's too many possibilities, then would you suggest, try to think of the complement?
Definitely. Yes, like earlier when I said, what's the probability of not getting a queen? That one's easy, where you can just directly think,
Right.
okay, not a queen, there's 48 non-queen.
Right.
But when one of them, when our options are a little bit foggier than that, when you're really not sure of which scenarios are possible or how many scenarios are possible, then you're exactly right. to work backwards and try and think, okay, I can't figure out this problem. Let's see if I can figure out the complement of this problem, and then use that to find this tricky item. Does that make sense?
Yeah.
So you're exactly right. So the whole point of this lecture is that occurring and not occurring added together cover all of the bases. And sometimes one of these is easier to find than the other. And that this is a little bit less obvious though here. And so these are the way that we worked through these problems to be able to come up with these formulas. So I hope that this has been helpful for you, and I hope that you go into lecture with a little bit better of a visual image of what we mean when we say not all and at least one. And I hope that you use this item in the future homeworks and exams.